Okay, thank you. Welcome. I hope you've had a lot of coffee. This is going to be intense. So this is an introduction to residuality theory and an indication of how intense it is. This is a picture of me the last time I spoke at this conference. I woke up that morning, I had a bit of a cold, okay, and I tried to cure it the night before in the bar, it didn't work. I woke up and I looked in the mirror and I thought, oh, should I shave? And I thought, no, I'll get away with it. And that was the last time I shaved. So this is the impact that the conference has had on me. And God knows what's going to turn up here if I'm back in 3 years' time. So we'll go straight to the crux of it. What is the problem? What problem am I trying to solve? And the problem is, why is software architecture so difficult? Okay. Paul, Ralph, and Tamara wrote a paper in 2016. They went and talked to a bunch of software architects and senior developers and decision makers about the structure in software. And they said, how do you make your decisions? How do you know how many components you should have? How should you know what functions live in which components? And almost universally, the answer was, we don't really know. It's gut feeling. It's kind of, depends on the blog I read, depends on what I've seen before, depends on my habits. We're not sure. Software architecture is difficult. Why is it difficult? Some systems that we work with, some things that we work with are ordered, okay? They're highly constrained. You can predict their future states. You can easily test them. When you test them, you see the same behavior over and over again. This is a shock if you've been listening to the narrative for the last few years where we talk about complexity this and complexity that, but software is ordered. Software is a predictable, mechanical thing. Some systems are disordered. They're loosely constrained, they're unpredictable, we don't know what's going to happen next. You can test them, but the test might change the system, and the next test might be different. Patterns change, or there are no patterns, or we see patterns that aren't actually there. So human and business systems tend to be disordered. These are two completely different things that require two completely different modes of thought, two completely different sets of tools to work with. And we're really good at the ordered part, right? Because it's part of our educations. We're mostly STEM people. We think in terms of logic and order and testing and verification and all those engineering skills that we've learned over a career. And so what we do is we design this little ordered box of stuff, and we make it do stuff, and we test it, and we're happy with it. And we're all very good at these processes. We're brilliant at this. And the sort of people who come to this kind of conference, you're experts at this kind of thing. And then we take our poor, innocent little software structure and we place it into this pulsating, complex bubble of stuff that we don't understand. And it's got people in there, and it's got businesses and markets and social ideas and economies and politics and geopolitics. And nobody knows what's going on. It's not predictable, it's not testable, it confuses us. And as an architect, as someone who makes the structural decisions in this software, because the two things are related, you've got to start off in here. And you've got to do your ordered technical, big O notation, all that stuff. And then you've got to bounce out here and you've got to deal with humans, horrible stuff, organizations, all of that. And then you've got to bounce back in. You've got to look at these things from the perspective of the other, and you're constantly bouncing around, and you're never really in one or the other. Okay, you're constantly in this liminal space in the middle. And you've got to get really good at switching these contexts all the time. And because of this, I call the systems that we work with as software engineers hyperliminal systems, because we're never still. We're always in the corridor. We're always running between these two rooms trying to reconcile these two very, very different things. And if you apply the thinking from one of these rooms in the other room, you very, very quickly get into trouble. Okay? So if you try to map people with UML, it goes wrong. Okay. And that brings us to the actual problem, which I call the problem of X. So we take our innocent little software structure with its random collection of components. We put it into this pulsating bubble of noise. And as soon as we do that, something pops up in the bubble, an X, an occurrence, an event, a series of events that we weren't able to predict, that we didn't know were there. And that's not because we're stupid or limited. That's how these systems work. There is no answer in Western science for what is this X. So X pops up, and it never pops up alone, does it? There's always lots of them. And they immediately start pushing this structure And it's at this point we discover the structure was wrong. The structure wasn't optimal for what was going to happen in the system. The structure that we built at time T1 no longer applies at time T2. We're in trouble. What do? We rebuild. So there are so many X's, though, in this bubble. So many things. All those things I talked about, our society, our attitudes, our team, our organization, the market, the economy. It's too much for us to handle. So what we do is we shrink this bubble and we use magical techniques. One of them is called requirements engineering. We say, oh no, you have to be specific. Stakeholder, tell me about the future that no one can possibly know so that I can build our system. Or we do risk management. I think there's a 0.37% chance that this is going to happen. Okay, 0.37 has no basis in reality, but as long as we shrink the bubble, we can feel comfortable and we can say, this X, and this X, that's what counts. We're going to build it, let's go. And everyone goes, yes, speed, velocity, go. We build it, we deliver it, boom. Another X that surprisingly no one could predict, and our structure is wrong. If this was the end of the story, then we would already know what to do, right? These unpredictable things are going to happen, they're going to destroy our structure. We can't predict them, we can't understand them, so what do? We give up. If this happens all the time, we just give up. And we say, look, when X pops up, we'll deal with it. Yeah. The problem is that certain software engineers and certain architects have to go and destroy this easy way of solving the problem by getting this right. And it's their fault that we have to think about these things. What happens? Why do some people consistently over the course of a career solve this problem? What are they doing? What are they doing that lots of other teams aren't doing that fall down when this X pops up? Are they lucky? If they were lucky, then we would see a spread over all architects, and we would all get it right 17% of the time. As it happens, there are architects who get it right all the time, and the industry gets it right about 17% of the time. Someone's doing something different. And this book by Donald Shun, which is from 1981, talks about the difference between technical rationality, which is using ordered systems and ordered thinking to solve problems, and reflective practice, which is being exposed to more complex domains. And there's a great deal in this book that describes what happens in the head of an architect who's able to solve these problems. But that's only looking at it in hindsight. The way that we deal with it is that we take a senior developer who appears good and competent and we just throw them in at the deep end. And we come back 5 years later and we say, did they drown? If they didn't drown, we have an architect. If they did drown, we push someone else in. We say, we'll see you in 5 years. We need a better way to solve this problem. And the problem that I'm describing is very obviously one of uncertainty. We don't know what's going on. We can't predict it. We are not in control of this thing. There are tons and tons of methods and ideas and methodologies that will tell you that you can be in control of this thing, or that you can embrace it or thrive in it. And once we look at the problem of uncertainty, then we turn to the complexity sciences, which is a natural thing if you follow the reading on this. How do I solve a problem when I don't know what the problem is? And I don't know how to solve it. And the problem with complexity science is that it's absolutely enormous. Okay? There's a lot. It's been going on for a long time. There's a lot of books, there's a lot of ideas, a lot of ways of thinking about things. There are very, very, very few concrete ideas that you can apply to software engineering. And I've seen this. You can go and you can listen to someone talk about complexity science, and it's fascinating, right? We're talking about networks and things that can't be predicted, maybe some bizarre probability, some cool math. But it never really ends up with, here's a concrete thing you can do in a system to design a software system in conditions of uncertainty. It's not really relevant to software engineering. And that's what I'm trying to change here today. And so residuality theory, at its base, before we apply it to software, it's just a way of thinking about complex systems that then turns out to make it easier to make decisions in conditions of uncertainty. So we have a complex system, a business system, let's say, and it's got all these nodes, and they're all tangled up with each other. They're all connected to each other. We don't really know how this system does what it does. They're all connected. We maybe don't even see all of them. We're not sure how they're connected to each other, but we have an idea about it. And all we can say is, if we're honest about what we can say and what we can see, is that something's going to happen. That's it. Okay, there's nothing else to it. And anyone who says anything else is trying to predict the future, and you shouldn't buy anything from them. When this something happens, the system changes. Okay? And we generally refer to that, because we're engineers, as saying the system is broken. It no longer does what it did before this X happened. The system looks a little bit different. And this little, probably damaged bit of the system we call the residue. This is what's left over when something unexpected happens, when that X pops up. And all residuality theory says is that this residue will continue to exist, and it will interact with different nodes in different ways, and there will be a future, which we don't know, we can't predict, we don't understand. But we can say that the future system will be a function of the residue. It will be built on the residue. So think about what we're saying here. We have a complex system, we don't know how it works, something's going to happen, we don't know what it is, and then a future is going to occur, and we don't know what that is either. It doesn't sound terribly useful so far. But what we can do, if we're engineers, and if our system looks like this, and it has this little ordered piece in here, we can impact the residue of the ordered piece. We, as software engineers, as designers, we get to decide, how does this thing fall apart? And this is our way in. This is how we can come in and actually do something useful in a system where, in all honesty, we know nothing about what's going on. And it's a pretty simple idea, and it diverges from a lot of the complexity literature. So it's saying that this system doesn't have a purpose, it doesn't know what it wants, it doesn't know where it's going, it doesn't have feelings. But it's a very, very simple idea. Things fall apart, and we don't know why, and then other things will happen. Not entirely controversial. So to tie this back to software and make it useful, we need to look at software from the perspective of the complexity sciences, and there's an awful lot of tools, an awful lot of ideas in complexity science, so I'm just going to show you two today that are particularly relevant to what we do as software engineers, and hopefully it will seem familiar. The first thing I'm going to talk about is something called random simulation. This is a standard concept in statistics. We have a square of side x, and we have a circle inside the square. We don't know if they're not concentric. We don't know anything about the distance of the circle from the edges. How do we figure out the area of the circle? We throw a dart at it. The dart hits the circle. That's data. We throw another dart at it. The dot lands outside the circle. That's data. So roughly half of our darts, or exactly half of our darts, have hit the circle, so we can make a guess, and we can say that the area of the circle is x squared over 2. It's probably wrong, but it's scientifically reasonable. It turns out that if you repeat this and you take lots and lots and lots of points, you can get really accurate measures of the area of the circle without ever using a ruler. So we're randomly simulating, we're randomly choosing points in the environment, even though we don't know anything about where this circle is. If you think about requirements engineering, risk management, they're just random points, random data points. They don't mean anything, doesn't mean they're true. Just because you ask a question and someone tells you the requirement 1.6.4 is this, or this risk has a 22% chance of happening, it doesn't mean it's in the circle. It's part of a random sample of the environment. It's all we can do in a hyperliminal environment, if we're honest. But the entire premise of requirements engineering and risk management is about, maybe not being so honest with ourselves and pretending that this works, that this is rigorous. Okay? That's something you can ponder on tonight in the bar. Another really, really, really important concept from the complexity sciences is the concept of Kaufman networks. So Kaufman was a biologist who studied complexity science and came up with some fantastic ideas and theories and models about how life actually came to be, how we emerged from a soup of proteins. and then got iPhones. And the way it works is that this network is a random Boolean network. And it's a Boolean network. So each one of these nodes in the network has two possible states. So a good way to think about these things is light bulbs, right? They're either on or off. And every single one of these nodes has a little function inside it. Not necessarily the same function in every node. And it executes and it decides randomly, am I on or off? Poof. Okay? And so if you flick the switch, some lights go on, some lights don't go on. You flick it again, different set of lights go on. The number of possible states in such a network is 2 to the power of n. And Kaufman ran his simulations for n equals 100,000. That's more states than there are atoms in the universe. Can you imagine the requirements document? Then he started to do some really interesting stuff. He started to connect the nodes, and he started to make each node's random function dependent on input from another node. He made the network interconnected. And then he got some weird results that he didn't expect. The system, every time the switch was flicked, would show a state. And he started to think, I've seen that state before. This is weird. It turned out that the number of states in a connected network was root n. So for 100,000 nodes, 317 possible states. Amazing. Our requirements document just went, oof. This is really interesting. So the nodes actually constrain each other, and they fall into a pattern of behavior that he called attractors. This network has a tendency to fall back to the same 317 states all the time. That's fantastic, because we're working with things that are much bigger than this. Much bigger number of n with a bigger number of possible states. They're not just Boolean. And this gives us hope as software engineers. And that leads us to develop something as software engineers. If we start to think about our components in these terms, this brings us to the idea of an NKP analysis. N is the number of nodes in the network. K is a measure of the number of edges in the network. So in this case, I've taken the maximum number of edges, which is 3. But it can also be the average number of edges. And an edge is just a line that connects two nodes. The third value is something called P. So if n gets really big, the number of attractors gets bigger. The system becomes less easy to manage, less ordered. As k gets really big, the number of attractors become much bigger, and the path to those attractors, the way the system moves to get there, becomes much more complicated. And so as k gets to 4 and 5, systems become chaotic. P is the bias of a node. And I can bias this node by making sure that 90% of the time it chooses to send a signal down this pipe to this node. And that biases it towards a certain course of action most of the time. We do this all the time in software engineering. We decide on n, okay, this eternal microservices or monolith, that's an n discussion. K is about coupling, obviously. And P, to implement P, we use schemas and contracts and rigorous error management to bias the system towards a certain course of action all the time. And so the conclusion from this is that every software engineer in every project actually uses a 2-step algorithm to produce their design. The first is a random simulation of the environment. They might not think it's random. They might think it's ordered and structured with requirements and risk, but it's a random, really. Followed by an NKP analysis of potential component structures. This is what we do in every single project that we've ever worked on in enterprise software. That makes it much simpler. The problem we have is that our simulations aren't random because we use these tools that are designed to take randomness away. And our NKP analysis isn't explicit. We tend to say, I use solid, or I use grasp, or I use this or that. We don't actually, we bury the NKP analysis in layers of theory and stuff. So we're not actually aware that we're doing this most of the time. And so residuality theory then, when we apply it to this mess that we're trying to solve, We'll make the simulation more random and the NKP analysis more explicit. And then we'll go on to prove that it actually makes a difference to what we're doing. And so if we go back to our pulsating ball of madness that we put our software into, what we can now say is that we don't need to think about everything. We have these things that Kaufman showed us. They're called attractors. And this network, because it's interconnected, it will have a certain number of attractors. If it didn't, life would be impossible. And what we do is we randomly generate some form of stress, some X in the environment, and we say, what happens when this randomly generated X hits our system? Well, then we say it moves our business system, our human system, to this particular attractor. What happens to our naive architecture, which is usually built for some kind of happy path attractor, where everything's easy? What happens to our architecture? What happens to our software structure? And we say, this one dies and this one dies. And the structure's no longer fit for purpose. That's our residue. But we're engineers. We're in control of this residue in the ordered system. That's the good news. So we go and we say, if we stick this green component in here into the system, this residue will survive, or at least survive in some form, inside this attractor. And we park that over here, and we say, that's residue number 1. And then we do the same thing with another random form of stress. It pushes us to a different attractor. And it requires a different component to survive inside that attractor. That's residue number 2. And we do it again, residue number 3. And we build up this massive stack of residues that describe the system as it should be built for different attractors in the environment. And what we're left with is a naive architecture, which we started out with, and a whole bunch of residues. And what we've got to do now is push all these things together into a coherent architecture where they don't destroy the ability of each other to survive in their attractors. And that's got some problems. Why does this work? It turns out that we're just leveraging the mathematics of these systems. So one residue, when we look at it, tends to support more than one attractor, generally. It's not a rule, but generally it supports more than one attractor space. Each attractor, in turn, has dozens of potential stressors or chains of stressors or happenings that can push the system into that attractor. These are all the X's that we have no chance of ever seeing, or ever knowing, or ever being able to list or capture in any sort of risk management protocol. But it doesn't matter. We only need to get one. In this entire group, one source of stress will bring us to one of these attractors, will bring us to the residue. The residue then will protect us from all these other X's. That's a significant return on investment. Why doesn't this work in normal cases? There's a statistical problem known as the curse of high dimensionality. When we try to do random things as human beings, we fail miserably. Okay? We focus on things that we think have a high probability, that are embedded in our past, our way of thinking about things, and we tend to focus on this, the center of the circle, things that have high probability that seem reasonable to us. You've all heard of Yagni, right? Yagni is the codified way of making sure that we stay inside this red circle. That's never going to happen. Using probabilities, random numbers that we pull out of the air, all of these things stop us from being random. When I was last here, I talked about the concept of lizards. So one of the first things you need to think about in your project is that giant fire-breathing lizards are going to come out of the sea and destroy the city that you live in. What's your residue? What's left over? Okay, and that seems nonsensical, and that's the whole point. It doesn't have to make sense. We're trying to be logical and rational and ordered in systems that are consistently rejecting rationality and ordered thinking. Lizards don't exist in the North Sea, and not the big fire-breathing ones, we think. And it doesn't matter, because lizards are this X here. And the residue that we build supports us if there's fire or flooding or a war or an invasion or a pandemic or an economic crisis or social unrest. Lots and lots and lots of X's get covered because we thought of something ridiculous. And every time one of our junior developers or one of our stakeholders says this might happen, and we say, nah, that's never going to happen, we're killing the lizards, okay? We're making our system less able to cope in the environment we're going to put it in. And here's an example, which is a semi-fictitious example. It's based on an amalgamation of a number of actual real-life projects. And so what we're going to do is we're going to build a networked system of chargers for electric cars. And the way the naive architecture works is you get a key fob as a customer, you drive up to the charging station, you hold up your key fob, a message goes up to the cloud, looks for your subscription, says, yeah, this is good, sends a message back down, and you start charging. That's the naive architecture, the happy path. And we produce a stressor analysis. This is a politically correct stressor analysis. When you're going to show these sort of things to management, you take out all the stuff about lizards. They don't like it. And can you read that text? Okay, we'll stay with this slide. So what's really interesting here, there's a couple of things that are really interesting. Stressor number 3. What happens when login fails? This happened all the time. These little key fobs were sensitive to temperature and magnets, water, and all of those things. So what's the residue when login fails? You have a customer, and this, at the time I was building this, it was Tesla's. So you have a wealthy customer, drives up, half a ton of metal, almost out of battery, holds up their key fob, nothing happens. Your residue is a half ton of metal in front of your asset and a very angry rich person. Not good. So how do we solve it? We need to solve this, and we change the residue. We add that little green component, and that little green component is something called ALPR, Automatic License Plate Recognition. If the person can't log in, we just take their license plate. In most jurisdictions, you can do this now, and we'll send them a bill later on. The cost of charging the car and letting them drive on is minimal. Okay, it's cents. And that changes our architecture a lot. The next thing that's interesting is number 8, or 8. As I should say when I'm not home. And that's damage. Accidental damage or criminal damage. Someone's going to drive into these things. Teenagers are going to spray paint them. How do we cope with that? Well, let's have some redundancy in our residue, and let's have security cameras. Number 12, big problem at the start. Someone turns up, plugs in the car, and goes off to play golf. Car stuck there for 8 hours. Only the driver of the car can unlock the chargy thing. Chargy thing is a very technical term. And how do we do that? Well, we actually go and we can use an earlier residue, which is ALPR, and we change the business model a little bit. We invoice them per minute. First 25 minutes of a fast charge, which gets you to about 80% of the car, that's a normal price. Next 25 minutes are going to cost you. 25 minutes after that are going to be extremely expensive. So we change our business model, we change our residue, we get to the point where we say, go ahead. Okay, it's going to cost you a lot. We'll get paid more for this asset, and the redundancy and stress in our residue for number 8 will cover that for us. That's not that spectacular a story, okay? This is normal business development. This would have happened anyway. Because we built the architecture like this, a while later, stressor number 14 shows up. And 14 is called icing. ICE stands for internal combustion engine. It started to happen in the United States. People would come in their pickup trucks and they would think, people are driving electric cars. That means that they have a certain political view of the world. And I don't like them. So I'm going to park my diesel pickup truck in front of their charger. And then they won't be able to charge. And I'll have won some small victory. That's one of those X's, okay? That's one of those social things in this giant pulsating bubble that we could never grasp, never understand, never see. But it turns out that a combination of our residues, 12, 3, and 8, you're going to be invoiced per minute if you pull up. First, because of 3, we're going to read your number plate. Because of 8, we have you on camera. We know who you are. We have a picture. We're going to tell the police. And stressor number 12, you can park there if you want. This is going to cost. A bill is going to come to your house for lots of money if you park there. for a long enough period. Plus, we've built in, because of stressor number 8, we have redundancy in our system, so go ahead. We'll take your money. This thing that we couldn't predict, couldn't see, couldn't possibly have known was there is solved because of this residual structure in the architecture. And this is just an example, okay? Like I said, it's slightly fictional. But this happens over and over and over again when you use this method to build your architectures. It's absolutely fascinating that it happens. Absolutely fascinating that people are starting to go, oh, what's happening? What did he say? So this happens all the time, quickly. It's absolutely fascinating. It's a much more fun way to build systems. And the reason that I'm describing these things is because I was asked at one stage when I worked at Microsoft to create new architects. And I said, what does that mean? And they said, make them do what you do. And I had to take a step back and say, but I have no idea how I do what I do. And when I analyzed what I did, I realized I'm just a negative Nancy who comes up with all these mad scenarios that's going to crash the system, and then the architecture kind of falls out of that. This is just a formalized version of that. If you thought this was an American problem, yeah. Munich last year, someone thought, electric cars, vegetarians. Let's stick some mincemeat in the charger. How many of you have ever had a risk register for your projects where you said, someone's going to stick mincemeat in it? You just don't catch these things, and it's impossible to even try. So the next thing we've got to do is we've got to push all these residues together. And if we just take all these residues and try to build them and try to stitch them together, it's going to cost a lot of money. It's going to be awkward. There's all these different contexts. These are essentially a bunch of different views on the architecture. So what we've done is we've followed all our best practices that we've absorbed over the years from various different methodologies and ideas, and we have this architecture. This is our structure, and we've protected ourselves from change, and we don't link components when we don't have to. It's loosely coupled, and we've encapsulated risk and things like that. But this is still just that ordered structure inside the crazy bubble. And a stressor will pop up. We know it's coming. We know something's going to happen because that's the nature of these systems. What happens is, and what's really dangerous for us, is that sometimes that stressor will hit two components. It will hit component C and component G in this architecture. And C and G in this architecture, I, as an architect, have decided these are decoupled from each other. There's no relationship between these two things. In network science, which is a hobby horse for complexicists, if you have a stressor and a component C and a component G, and the stressor has a relationship to C and the stressor has a relationship to G, it implies a relationship between C and G. There is coupling in this architecture. And we couldn't see it, and we won't see it. We won't see that coupling until the stressor pops up. When the stressor pops up and we try to fix it, then we've got to go back to the project and say, this is going to take 6 months. These things are coupled, we didn't know. That's what makes our job hard. It turns out when you work through these stressor analyses that you find these hidden couplings constantly. They're always there. And you end up with this invisible spider's web of connections between your components. This is why our jobs are hard. This is why the structure falls down when an X pops up. All these links are here, and they're really, really difficult for us to see. And it turns out, because we're pretty good at seeing functional links between process steps, that we generally don't, this kind of coupling isn't functional. This kind of function is generally related to the non-functional. And so my consultancy work is mostly focused on rescuing crash projects. Most crash projects fail because they miss non-functional requirements. Non-functional requirements are missed because of this invisible spider's web. So what we're going to do is something called contagion analysis. So we're going to integrate these residues and prevent contagion. And we're going to base it on the Kaufman analysis, the NKP analysis that we talked about. And we're going to consider our system in terms of stressors, Flows, which is just information moving between one actor and another. It's a way of not thinking about processes first, just information that moves. Functions and components. And functions are software functions, and components are groups of software functions. And there's three types of coupling we want to figure out. Dependency, interdependency, and this hyperliminal coupling, the one that hurts us. And the way we do this, because remember, we're talking about networks here. These are networks, nodes linked by edges. And the way that we work with networks is through matrices. And so the first thing we do is we build a bunch of things called adjacency matrices. And this is just mapping out the links. And you can see here, this is a very simple matrix of across a bunch of different functions or flows. And what the pattern you can see here, this little diagonal of ones, this is a call chain. This is nice and ordered, okay? If you add up the number of ones in this matrix, that's 3, divided by the number of flows, which is 4, you've got k of 0.75. This is incredibly ordered. This will not cause you major problems, hopefully. However, if we look at this mirror, these are bidirectional matrices, and we start to see that components are dependent on each other, and we'll see that in this mirroring of the one over this line in the middle, then we might have a problem. Okay, we've just doubled k. And this can be a feedback loop. This can be honestly a good thing. It can also be that we've misunderstood the business process. It can also be that we're trying to do too much in one component or one process. This can get out of hand. We call this complexity, so k starts to increase massively as we have lots of interdependency, and then we end up with a Markov system where anything can happen, any point can jump to any other point. K is incredibly high. There are actually business systems that work like this, but thankfully they're rare. The next thing, and possibly the most important thing that comes out of all this, is an incidence matrix. And the incidence matrix works like this. We take, in this case, our flows or our functions or our components, and we make a list of all the stressors that we came up with, and we have all our flows here. And we go through this, and we give it a 0 if the stressor doesn't hit that particular flow or function or component, and a 1 if the stressor does hit it. What does this tell us? When we see that a stressor is hitting lots of different things, that's coupling. So we go back to our adjacency matrices and we say, do they have a coupled relationship in this matrix? If not, we've discovered a non-functional requirement. In this case, it's a server failure, and the non-functional requirement is obviously availability. But this is a very thorough way of finding out what are my non-functional requirements in this system. Okay, most of us use a checklist, right? Go to that Wikipedia page, give me the list of 60 non-functional requirements, and we make 2 up for every title. Other things we see that this one has a very high number. We take totals. Okay, that's high K. This stressor is generating high K. It's an indication that there's a problem in the architecture. We need to take care of this. And we can also look down here and we can see that some of these things have, here is a high K for this particular function or command or flow. This is also dangerous. And this is a signal to us, refactor. Okay? Change your idea about the flow, change your idea about how these things happen. A little interesting note here is that we see that there's a 1 for the stop charge command and a 1 for the unlock car when the stressor is that the servers fail during a charging session. Those 2 components, the stop charge command comes from the cloud. The unlock car command is embedded code in the charger. They're written by 2 different teams. If the server failed while the cars were plugged in, they'd be stuck until the servers came back up. This kind of analysis helps us catch that hyperliminal coupling across things where we hit it because of our team structure, because of our technology. Another really interesting thing that comes out of this matrix is that for those components like this one and this one that have exactly the same reaction to stress in the environment, okay? And you can find these things mathematically. This is where it gets really cool, and I'm sure there's some machine learning people in the room getting excited. If they have the same structure, they belong in the same component. You can put them in the same component. You're going to have to go and change both of them anyway. These things get to live and die together. Another even more interesting thing to look out for is structures that are almost the same. Because structures that are almost the same, we tend to say they belong in the same component. That's our gut feeling. That's how we do our normal everyday job. That slight little variation, that 1, 0, or that 0, 1 in the second row, tells us that something's going to pop up here and hurt us if we live on this assumption. And if you add all of these and all of these and all of the ones in your adjacency matrix and divide it by the number of things you're working with, you get an approximate value of k. It won't ever be accurate because we can't see all the nodes. But if k is bigger than 3, refactor, you're going to have serious trouble deploying and managing and changing this thing. Really, really simple heuristics that come out of this thing. The final thing that we do is when we've done all this work, is that we run a little experiment, a little empirical proof to show our stakeholders and our teammates that, hey, we did something useful, which is a new thing, a new concept for architects, I guess. We have a naive architecture, and we have a bunch of stressors, and we use those stressors to produce our residual architecture, and we use our matrices to make component decisions. And what we do is, we don't use all of our stressors. We keep half of them in a drawer for later. And what we're doing is we're using a kind of training set, testing set concept here. Now we're going to run these red stressors over the naive architecture. If the naive architecture survives the stressor, survives in that attractor, we give it 1 point. If it doesn't survive, it gets 0 points. And then we get a number, x. And we do the same thing for the residual architecture. If it survives the stressor, if it survives that attractor, it gets a 1. If it doesn't survive, it gets a 0. And if both of them get a 0, we look at that stressor and we say, which one survived the best? And it gets a 1. And then we run a little calculation. It's called the residual index, y minus x over s, which is the total number of red stressors. And this gives us the residual index, which obviously is between -1 and 1. If the residual index is greater than 0, you have a system that demonstrably is more likely to survive unknown forms of stress than the naive architecture. You have done work as an architect. You've moved things forward. And you'll find that if you loop through this a couple of times, you can push that RI higher. If you're brilliant, if you're a genius, one of those genius architects, RI will always be 0 because you've already thought of everything. If RI is 1 and you haven't thought of anything, that's a signal too. But generally, what I've done this with dozens of groups across Europe, and RI is always greater than 0. And if I can show in my research, which will be published hopefully early next year, if you can show that this holds for a big enough number of projects, then it's statistically it's significant, yeah. Statistically significant. Then we actually have something here. It's a workable scientific theory. And we will have a tool, if this is shown to be true, we will have a tool that moves us from intuition as the key skill of software architecture to something that looks much more like engineering. And this empirical proof is the thing that lets us escape from the fact that the stressor list is subjective. It doesn't matter that it's subjective if we show that we've done real work. After that, we don't get to escape our responsibilities. There's still a bunch of systems engineering to be done. There's a lot of internal stress in these systems. So things like, you'll get 90% of the way with a simple failure mode effects analysis. But standard architectural tools, good testing strategies, ideas around scale handling and telemetry, keeping that focus on NKP all the time. And so what we actually have here is a new theory of software engineering. And it's new, so that's going to upset some people. But the difference is, this is grounded in the complexity sciences, but this actually provides concrete tools to software engineers. And so what we're doing is we're designing how we want our system to behave, and we're discovering non-functional requirements. This stuff is properly researched, and so the last time I spoke here at DDD in 2019, I had a bunch of ideas about these things. I was starting to articulate them, and I decided I don't want to do the standard talk at conferences, sell consultancy hours way of doing this thing. I'm going to go back to school. And so this has become the subject of a PhD. This is being put through the ringer, okay? I want to make sure that this is actually true, rather than just making statements on a stage. This is compatible with everything else you do. I'm not asking you to stop doing anything. You can do things exactly the way you're doing them in your organizations today. Take a couple of minutes out, draw some matrices, think about some lizards. Watch, things might improve. And this is for software engineering, okay? This is not for management consulting. Okay? You don't design businesses, don't design organizations, don't design your societies or your house based on these ideas. They only have a mathematical leverage when the system is hyperliminal. And software is definitely hyperliminal, but what you're designing is a human organization, N is very high, and that mathematical leverage disappears. So please don't apply this to things that it doesn't apply to, because you'll discredit the idea. There's been a bunch of stuff written about this. I've heard from some people, like Cyril, that it's very heavy, and it is very heavy. A lot of these articles are based on getting these ideas out there into print so that I can say I had these ideas first. There's even one that's ended up in a philosophy journal, much to the horror of my professor, my mathematics professor. Today's talk is based on this paper, which came out this year, Residuality Theory, Random Simulation, and Attractor Networks. And these are free to read on the web. And you can reach out to me here. This is the final slide. And hopefully this has been useful. Hopefully you'll be able to employ and use the ideas. There will be a book and a PhD thesis. Hopefully in the beginning of next year. I've made promises before that I haven't kept, so we'll see how that goes. And thank you for listening, and I'll see you out there.